Hello and welcome back to Algebra, the video series where we talk a lot about algebraic structures like groups. And indeed, in today's part 12, we will talk more about subgroups, in particular how we can form subgroups with homomorphisms. But as you already know, first I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter and with the link in the description, you can download additional material for the videos. Okay, then let's start by considering two groups G and H again. Both can have their own binary operation, and we already know what a group homomorphism between both groups means. Namely, it's a map phi that conserves the binary operation. In a formula, this reads phi of A with B is equal to phi of A with phi of B. So in short, you can say in a group homomorphism, we can pull out the binary operation. Okay, but we have learned in the last videos that we can also have subgroups in G here. So we would say, here we find a group U with the same binary operation. However, if we just look at the set level, then U is just a subset of G. Therefore, we can also look what happens to this subset when we apply the map phi. And then you know, on the set level, we call this the image of U under phi. And as a common notation, I always use brackets to denote this subset in H. So this image here is well defined as a subset in H, but now we have the natural question, is this image also a subgroup in H? And I can already tell you, exactly this we will prove in this video. Moreover, I also want to go from the right hand side to the left hand side, which means we could also consider a subgroup in H here. This means we have a subset V here with the same binary operation. And now for every map phi, such a subset V has a pre-image in the left hand side here. So this is exactly the subset in G where the points are sent to V by the map phi. So again, without any problems, this set is well defined on the set level. And the notation we use there is phi to the power minus 1 of V. And again, I use brackets to make clear that we are talking about sets here. And the common name I've already told you, it's called the pre-image of V under phi. So it's well defined as a set, but now the question is it also a subgroup in G? And in fact, the answer is yes as well. We can prove that the pre-images of subgroups are subgroups again. The only requirement we need is that we have a group homomorphism. Therefore, let's immediately put this nice result into a proposition. The overall assumption we see in this picture, so we need two groups and a group homomorphism phi. And then we can look at a subgroup U on the left hand side and at a subgroup V on the right hand side. And then we have the following two results. Namely, the image of U is a subgroup of H and the pre-image of V is a subgroup in G. So this is a general result. A homomorphism always translates subgroups to subgroups. And now before we look at important examples, we should definitely write down a proof for this general result. And it turns out that this is not so complicated at all. So I would say, let's start with A. So we take two elements from the image of U. So let's call them A and B, so we know these are elements in the group H. So in the picture before, they live on the right hand side. Which means we find corresponding elements X and Y on the left hand side. In particular, we find them in U such that phi of X is equal to A and phi of Y is equal to B. So there we just use the definition of the image. And now we can just calculate, so we look what A star B actually is. And now what we want, that this lies in phi of U again. Hence in the first step here, let's substitute A and B. So we get phi of X star phi of Y. And exactly at this point you should recognize that we can use the property of a group homomorphism. To say it in a sloppy way, we can pull in the binary operation. So in this case we get phi of x, y. And now please note, before we had the binary operation in H, and now we have the binary operation in G. Moreover, we also know that U is a subgroup in G, so x with y lies in U again. So this is an element in U because U is a subgroup. Hence, here we also get that this is an element in the image of U. And this is exactly what we wanted to show. A star B lies in the image. So the conclusion is we cannot leave this set with the binary operation. And this is already one of two parts for showing that we have a subgroup. And the second and last part is that we cannot leave this set by using inverses. First of all, the inverse of A is well defined in the group H. But now we know we can also translate it to the group G by using the map phi. So here we have the inverse of phi of x. And now please recall that we have shown in part 9 that we can pull in the inverse operation if we have a group homomorphism. So there we have the inverse of the element x, which is well defined as an element in G, but we also know it lies in U because U is a subgroup. So you see, this is exactly the same reasoning as before. And now we have also proven that we cannot leave the image by using inverses. Moreover, you know these two things together are sufficient for having a subgroup. This is exactly what we have discussed in part 10 before. And with this part A is proven, images of subgroups are always subgroups if we have a homomorphism. Hence, in the next step, we want to show the same thing for preimages. And there the logic is the other way around. Now we have to take elements from the left-hand side. The preimage lives in the group G, and now we want to show that we cannot leave this set by the binary operation and by inverses. Indeed, we don't have to change much because we also find corresponding points A and B on the right-hand side. In particular, now A and B lie in V. And that should satisfy that X is sent to A and Y is sent to B. Again, this is exactly given by the definition of the preimage. And now we want to show that X binary operation with Y is also an element in the preimage. This means we simply have to check if phi of this element also lies in V. Again, this is simply the definition of the preimage. Every element that is sent into this set V has to lie in the preimage. Therefore, in the calculation, we don't have to do much. We just apply our homomorphism property, which is phi of x star phi of y, which is also A star B. And now we apply the same reasoning as before. V is a subgroup, so A star B lies in V again. So the conclusion for this equation is that x with y lies in the preimage again. So we cannot leave the preimage with the binary operation. And now, not so surprising, we want to do the same for the inverses. And then we have the same calculation as before. We get out A inverse. But A is in V, so the inverse is also in our subgroup V. So we get the same conclusion here. X inverse has to lie in the preimage of V. So for the last step, we just have to say again that these two things are sufficient for having a subgroup. And there we have it. This is the whole general proof. And you might already know, this proposition is something we want to use a lot in future. And indeed, I can already tell you two important special cases of this proposition. It's about the so-called kernel and range of the homomorphism. So not so complicated, we just have a preimage and an image as a special case. In fact, we know that the identity element E always forms a subgroup in H. So the preimage of this set with one element under phi is definitely also a subgroup of G. And this special subgroup is called the kernel of phi. So definitely something you should remember, and it has this short notation there. So you can remember here, everything that is sent to the neutral element in H forms a subgroup and it's called the kernel. On the other hand, we also know the biggest subgroup we have, and this is just the set G itself. Therefore, we can also look at the image of G under phi. So this is the largest image we have. And therefore, I usually call it the range of the map phi. However, another common notation for this is to say this is the image of phi. And there you also often see the short notation Im of phi. And indeed, there's no difference, it means exactly the same thing as range. So the image of the whole group G is just called the image of phi. And again, both subgroups we can visualize in the picture, so we have G here and H on the right. And now the kernel of phi you find here as a subgroup in G, and the range of phi we find on the right hand side in H. In fact, here I should already tell you that in future videos we will often consider subgroups that are given as a kernel of a homomorphism. And maybe in this video we can already look at a simple example. So let's consider phi that comes from the group Z with the addition and maps into the simple group with just two elements. So let's call the two elements E and A. And now let's define phi by saying that K is mapped either to A or E. And I want to map it to the identity element E if K is even. Hence, if K is odd, we map it to A. And now with this definition, you can easily check that phi defines a group homomorphism. And please never forget, this means if we have phi of K plus M, then this is equal to phi of K together with phi of M. So here the circle denotes the binary operation we have in our group with two elements. Okay, and now the question I have here is, what is the kernel of phi in this case? So by definition, these are all the elements in Z that are sent to E. So in short, we just have all the even numbers here. And the common notation would be to write 2Z. So we get that the even numbers form a subgroup in Z. And moreover, this subgroup can be written as the kernel of a homomorphism. Okay, this is good enough for today. Let's meet in the next video where we will discover more properties of subgroups. So let's meet there again and have a nice day. Bye bye.